with no further ado, this is my talk on socio-technical systems. The goal of these sort of designs is to sort of achieve communities which are interconnected, they enable coordination, and effectively there's a degree of self-sovereignty associated with building stuff that allows us to interact with each other without sort of appealing to these centralized platforms, and yet we still get the sort of platform-like effect where we can do things with one another that we wouldn't have otherwise been able to accomplish without some sort of service being provided. Any case, the reason that this is really hard to do is because there's this like paradigm where we actually build stuff and it changes the way that the sort of world we live in works. Like there's some set of rules in the world that say, these are the things that I can do, here's what happens when I do them. But if we modify those, the result is that the way we ourselves behave changes as a result of the fact that the world, in a sense of what we can do, changes. And so this does result in a system where we have this, incentivization superpower, as Trent likes to say, but it also creates a world where we're not exactly sure whether that sort of incentive machine is going to drive someone to maybe sort of trade something that needs to be there for the thing that's being incented. And so in the optimization paradigm, you have both the optimization objective and the system constraints. We talked about that earlier today. And one of the most important aspects when you have people in the loop is to make sure that we don't sort of myopically have our system sort of evolve in a way that is actually violating some underlying constraint that needs to be retained. And that can happen. We often get unexpected outcomes. So what makes this hard is generally this closure over human behavior that is pretty much always going to be unknown to some degree, and the temporal dynamics in the system. I will like to sort of bring things back to a stack, since in the last talk we discussed stacks. In this engineering world, we can look at stacks as well. We go all the way from this sort of low level in the electrical engineering perspective, from the creation of semiconductor materials up through microchips and then microcontrollers, all the way up through motors and airplanes and an actual air traffic network. And if you notice, we've eventually reached the sort of socio-technical system where the human behavior starts to become involved, and actually there are teams of operations researchers making decisions about the way prices and capacities and everything in these networks of companies providing air traffic services. I'm going to a conference next week after DevCon in the US to actually meet with and talk and speak on with decentralized companies who've been designing these market systems for these big ecosystems for their careers. And in fact, there's more in common in the operations research management science field than we think sometimes, because there are versions of decentralized problems. They're just not at our level. The humans interacting, they're at the businesses interacting level generally. It's actually kind of exciting to bring it down to, to say, the people where we're building things for us to interact as opposed to for companies to interact. I find this really enthusiastic because it means that the paradigms that we've created for engineering actually sort of make sense in the blockchain systems context. And in fact, I think of blockchain itself as being a sort of semiconductor level technology, that our smart contracts and protocols are more at the microcontroller level technology, and that as we do token engineering, we're designing these ecosystem level technologies. And so it's not necessarily a one-to-one mapping, because I'm describing sort of the bottom level, sort of the middle and the top, which is nice. It's a slightly shallower stack, but we've got a lot to fill in. The thing that makes it a little tricky, though, is maybe it's a little bit wider. We have to basically be able to account for the social, the economic, the physical, and then the sort of technological, the software systems that are involved. And I tend to break these systems down into a different kind of stack here. This is a little more abstracted, but it allows us to think about how blockchain and blockchain-enabled technologies roll up to sort of an ecosystem level solution. In this particular diagram, I always start at the top and think about the desired global emergent behavior. That's what your your users or your communities hoping to experience, but then we define requirements and work our way down through, well, if that's what we want to happen in my ecosystem, what kinds of interaction patterns do I need to enable the behaviors that I want to see, the incentive machine maybe. Also, what kind of constraints do I need to make sure that the system doesn't break itself? And I work myself down to, okay, well then I need a source of secure computation, I need a source of trustworthy data, and that's where you get down into sort of the smart contracts and eventually to a blockchain platform. When I talk about that, this sort of relates to some specific elements of work, and I can discuss this whole range, but I tend to favor the left side here. That's the part of the system where we define the interaction patterns and where we sort of study the expectation of the emergent properties of those interaction patterns under some sort of models or beliefs about the behavior of agents. And in some cases, if you use formal methods in sort of with an analogy to the electrical systems, you can even do sort of worst case analysis. You sort of leave the notion of what people will do as a function and say, well, they can do any of these things. Let's test the worst case scenarios. Let's test the conditions under which the system might break. This is a sort of system level sort of threat analysis. It's a system level sort of safety type of considerations. And I generally favor what can happen over what will happen as the sort of first priority in designing these systems. We want to exclude from the space of things that can happen, things that we consider failure modes, and then we use our incentives to allow people to sort of evolve the system within its own feasible space. And if we return to the optimization paradigm, we're basically saying the humans are the optimizers, the incentives are the objective, but these system safety constraints are sort of baked into the cake. So another really important paradigm that was brought up earlier is the sort of difference between science and engineering. And in fact, those are incredibly complementary skills. I would go so far as to say you can't truly be the best analyst of a system if you haven't also had some experience designing those types of systems and seeing how your designs resolved into behavior, and vice versa. You really can't be a great designer if you also haven't really examined the outcomes of other designs and explored the design space and looked at what has come of that. We're in a very new field, so there's a limited degree of experience. We have to look outside of our field to find places where systems were designed and the eventual outcomes. Or we can actually, as this sort of community takes root with the Ethereum platform, a lot of people have built things and we have behavior and we can collect data and we can do empirical economic analysis. Basically, it's data science. It's our first sort of order: collect large volumes of data, look at the way the mechanisms work, and then actually explore how those mechanisms resolved into system behavior. I tend to sort of do this kind of work with my team. This synthesis diagram is the one that I drew up for the open source project Autonomous, which was originally proposed by Simon de Louvière, and there's a team sort of contributing to a repo on GitHub to try to bring this thing into being. And so with my team, we did some system level design here, and the upper example is some analysis done on real data from the behavior of users, as well as just general agent actors in the back end of the CryptoKitties ecosystem, sort of pull the data, explore what's happening, what can we learn? In that particular example, we found a sort of class of behavior that emerged that wasn't originally planned for and fulfilled a niche in the ecosystem. When we think about engineering, this is one of the first things that comes up. It's a validation and verification V. The idea is that you work all the way from your sort of global system requirements that represent what you're trying to accomplish, and you work your way down, breaking the problem down sort of subsequently into sort of well-defined elements, subsystems, eventually components, over which you can do pretty rigorous design iterations and actually evaluate your design even before you get to the level where you are going to fabricate your design. In the EE setting, that's simulations that you're going to run in a CAD tool before you actually print and test a prototype of the live circuit. In the engineering setting here that's running these system simulations before you code up and then sort of invest in generating the Solidity code tends to be a little bit easier to do rapid iteration over a set of differential equations than it is to iterate over the actual code base that's going to be live on a test net while you're doing experiments, though you do want to get there. We sort of stop to think about what it means to say that the system can be modeled as a differential equation. It means that there's a sort of system that evolves over time, and that the state of the system influences the future state of the system. And in fact, this is a paradigm that is widely used in all of engineering systems, but it's a little tricky to bring it to bear when humans are in the loop. And the way that we manage this is we say, actually, the system design itself is the plant. It's known to be what we designed it to be. But there's this feedback loop through what would in engineering be a controller. But ironically here, we don't have control over the controller. The controller is controlled by the public. It is people's actions, their response to the state of the system, given a set of actions available to them through the mechanisms that have been designed. But as it turns out, this field is actually incredibly good at dealing with unknowns because it's for building things in the real world where things are often inherently unknown up to some degree. And so what we do is we imagine this system as a known plant that we've designed and an unknown feedback loop that is limited by some well-defined action space, which brings us to a mathematical paradigm that is sufficiently consistent with sort of controls engineering to allow actual differential equation-based simulations. So our simulation sort of scientific approach at BlockScience involves starting with the sort of high-level sort of subpopulation models combined with differential equations that match the current design, which allows us to iterate designs and then sort of progress across this map as we get more confident about those designs from those simulation-based tests. Moving from sort of population level models, you can use the same differential equation-based model of the world to connect to an agent-based model, but it's still a proxy for the system to be built. But again, this is actually how we design systems in the physical world. We have models of them that are not perfect, but they are good enough to allow design iterations. And when we're confident, we move on with prototypes and eventually production-grade versions of those systems. And so we replicate that here by transitioning from our differential equations to testnet implementations of the code itself, and we would compare the results from the testnets to the differential equations models. And one of our internal projects, we've already been doing the direct comparisons between some of the error accumulations from sort of mathematical computations that are done on large integers compared to their floating points, because that's one of the main points of inconsistency. Our blockchain applications have very large integers that sort of represent floating points, but our sort of mathematical models assume real numbers and thus have some little bit of imperfection, but that shouldn't scare us because that's exactly, again, how the real world works. We have precision in our sensors, precision in our actuators, and the models are perfect at first pass, and then we move forward to account for the noise, the inconsistency, the missing information, and we make them work anyway. So as Trent said, engineering is the discipline for making things that work, and control engineering is the discipline for making things that work, even though you don't know a lot of stuff that you wish you knew. In any case, the practice here then goes through a very scientific engineering iteration. We have the sort of base theory, the simulations that allow us to sort of evolve our designs, and the empiricism, the measurement that allows us to sort of further refine those. And these go through a loop, a process that is defined by meeting requirements. It's, in a sense, test-driven, but it's there's a hierarchy of types of tests ranging from analytical proofs of properties over the models in theory, the simulations demonstrating that those properties hold in the models when they're implemented, and then the actual empirical tests on the code in production to further validate that the system works in life. So we're going to do a little bit of an example. So I'm going to use this autonomous map to sort of provide an example. We're not going to try to model this whole system because it's actually a very large circuit involving many mechanisms, and it would take a very large number of states and actor models and way more than we could ever go through. So we're going to zoom in and look at one pair of mechanisms, 2 internal states, 2 external states, and 2 behavior types. So in this case, it's going to be basically over these 2 mechanisms. One is a deposit, which causes the mint of a token. The other is a burning of that token that causes a withdrawal. This is a bonding curve in a pretty simple case. We define those bonding curves in terms of actual analytical functions that represent the quantity that's conserved under the mechanism. So in the case of the withdrawal, we're actually conserving the ratio of the token that is in reserve with the token that's being burned. And in fact, we argue that in this example, it would make sense to actually have both the input and the output function, the bond and the burn, follow this same invariant. This actually guarantees that if you bond and then immediately burn, you get back what you put in, less the sort of gas fees. And one can design these things to not match up, but that immediately lends you to discussions about these sort of sequential compositions of the different mechanisms. And in controls, this would be a switching system where you have one set of dynamics, and then you do something that follows a different set of dynamics. And so you could have any sequence of events representing, in this case, transactions, which follow the rules of a well-defined mechanism. So you have to be able to account for all possible sequences of legal actions, which quickly leads into very difficult territory if you don't actually have the mathematical equipment to make some analytic assertions about what is reachable. So you don't want a situation where you have 2 separately sort of well-defined mechanisms, but you could mix them arbitrarily to create dynamics that you really don't want. And you address this by working backwards from requirements defined as mathematical properties, and then showing specifically under which circumstances those properties can hold or change. So in this case, we actually have a system where the ratio of the pool and the supply can't change. So no matter what we do in all of the legal actions, if we only have these two, is going to preserve the ratio of the sort of supply of tokens with the reserve of Ethereum. Obviously, this only holds if these are the only 2 mechanisms, but that's our example. Our tooling for actually building simulations requires a representation of a tensor field, which is really scary until you sort of break it down into parts, and we can think of it as lots of pairwise grids. The grid between that encodes the policies of the agents with respect to the mechanisms, but doesn't really immediately care about the states. It's a function of the state and returns an amount of action over a mechanism per group of behaviors, which in turn gets the results of which get plugged into the amount of state change that occurs as a result of the amount of action. And so you get this system that sort of becomes a composition of easier to specify things rather than what in this case would have been like a 2 by 2 by 2 by 2 grid of nonlinear functions, because you have 2 states by 2 mechanisms, 2 behavior groups by 2 mechanisms. You've got two external states by 2 external processes, and then you've got the linkages between the policies themselves and the states. And so in order to actually map out all those functions, you would need to sort of break it down into something that a human can reason through. And in fact, I did this last week with Fong from Ocean. He lives in the Bay Area, and he came over to my home office, and we said, hey, I'm going to do an example for this talk. Let's like write down the equation. So I'm not going to try to map it out for you, but the idea is that people who have the visual design and know how to sort of work through differential equations could actually make a mathematical representation. Now, I will say that this is the thing that gets iterated over, so you're not done. You're actually at the beginning. Because once you have this, you can plug it into a simulation engine that knows how to read it, very much the way that you would do in a CAD tool if you were an electronics engineer. And so we plug in our Python script, which is literally a list of definitions of functions, which is all the math that was on the last whiteboard, and we run it, and we get plots. And in this case, I'm doing the IPython kernel inside of my IDE, but I actually generally would do my experiments in these notebooks because the simulation engine actually just outputs data, and if I want to do a data scientific exploration of my simulation results, I'm going to want to do that in something like a Jupyter notebook so that I can sort of explore. Now, so far all I've described is I made my system and I did one run. That's not engineering. Engineering requires an actual scientific iteration process. So we've actually been working on fleshing out these use cases. We're our own internal client. We use these tools for ourselves. And we are, we've got implemented the Monte Carlo version where it runs a bunch of times over the same test so that we can do analysis of the statistics instead of analysis of just one trajectory. And the new features that we're adding in the upcoming sprints include streamlining running pairwise tests where you actually have two separate configurations where you just run both, and then you actually have data that you can compare. Well, okay, essentially it's an A/B test. The interesting thing is that these are highly nonlinear complex systems, so you get a huge difference from something as simple as changing the initial conditions between the two configurations, because like if I start the same complex system at a different point, I could get a completely different trajectory. Or we could change our assumptions about the behavioral models, or we could make a design change in the plant, and we could run pairwise tests. We further consider a concept called sensitivity analysis. We can use parameter sweeps where we run a bunch of different runs with slightly different values of coefficients in these equations and see how much the results change. And this is generally a common practice for anything that's really not that well known. So you really don't want a system that's sensitive to something that you really don't know if you're right about it. So it's actually a really important system safety constraint to say, well, if I don't really know this for sure, let me see what happens over a wide range of values of this thing and make sure that I still get the intended results, even if I'm totally wrong about what this parameter is. So the less sensitive the trajectories are to a particular coefficient in your system, you can say that you're more sure, or this design is more robust to variations in that assumption or to that parameter. So the last sort of part in this section is I really only took a little piece of a system, and it's really important to remember that you don't actually do that. That's not how this works. If you take a little piece, it tells you almost nothing about the whole. The point of this, and much like circuits, if you take a little part of it, sure, you can successfully analyze that little part, but the properties of the circuit really come from all of the interconnections between all of the parts, and you can completely change the way the system operates just by adding something in parallel or in series. And here we have to think of these maps like they're these circuit diagrams, and we really have to get the whole thing mapped out in order to have our differential equation be particularly meaningful. For example, in my example, we conserved the ratio of the revenue that was sort of stored, or the amount of funds that were stored in this pool relative to the supply of tokens. But the moment that you have a mechanism like the sale of art that actually adds Ethereum into the pool without adding more of the SOL tokens, you actually create a net increase in value in the invariant because there's now more Ethereum per SOL in the supply, and you can think of that as sort of a shared profit, or a profit of the autonomous entity of which you have a share. So and as one would continue to fill this whole thing out, there would be more and more mechanisms, more and more roles of sort of people or bots interacting with the system, and that 2 by 2 by 2 by 2 grid could quickly become a 8 by 6 by 7 by whatever, and that creates a pretty complex system. And it's very much the reason why we need these tools. Like, we might have been able to sketch through this by hand or do an ad hoc simulation of the 2 by 2 by 2 system, but the moment that the system gets to the sort of complexity of an ecosystem, we actually really can't even hope to sort of make a simulation in an ad hoc way. I wrote a lot of ad hoc simulations early in my company, and that pain point was real, and this tool is very much a byproduct of streamlining that need and knowing the math to get it into place. And so I'm actually I'm pretty excited, just sort of direct people to the general complex systems theory, which tells you about the sort of non-additivity of these subsystems, that it's really a whole is greater than the sum of its parts. So with that in mind, I'm going to sort of go through one more section of this talk about engineering responsibility, since we've added tools that allow us to have a little bit more rigorous claims about what's likely to happen, what can happen, and the reason we need that is so that we can follow the other part of the engineering practice, which is thinking not just about what you can do, but what you should do, and its implications on the entities, the humans that ultimately benefit, or even sort of the planet as it happens. So we'll bring ourselves back to this notion of socio-technical systems, where we have this tight feedback loop between the world we're creating and our behavior in that world, and we just have to acknowledge that there's a high stakesness to these systems that didn't sort of live in Web 2.0, because removing them is hard or impossible. Changing them is hard. Not generally impossible, but often requires its own coordination problem, a governance problem, whether it's off-chain or on-chain, that's very much open. So we can't immediately assume that if we learn later what we should have done, that we can miraculously change it to that. Also, what I think we should have done and what Dimi thinks we should have done might be different. So even if we both think we can change it for the better, it might not change. So there's a really, really high stakes associated with your original design. And that's not to say that we shouldn't evolve it, but we should recognize that much like our hardware systems, we have to really be rigorous about our design process in proportion to how hard it is to actually make a change after we've deployed. So I want to make an example of a case where a system was designed for some reasons and it had a sort of socio-technical unintended consequence. I find this example to be sort of easy to understand because most of us probably experience it. So ride sharing came into existence. It was sort of a augmentation of our existing sort of cyber physical traffic network, where we were taking transit or we were driving our cars, and now all of a sudden we can have someone else drive their car to take us where we want to go, and this is great, and I stop using mass transit. And actually, when you think about that at a bigger scale, well, everyone has been provided the same new action that I have been, and a large number of people have made this change. And the net effect is that in a lot of cities, the total use of mass transit went down. And in fact, that creates more congestion. It adds to pollution creation. And even if our stated objectives had been around the ease of transit, mobility, if we hadn't really thought all the way through the way that system is interconnected with the rest of the world, we might have completely ignored its impact on something else that we cared about or should have cared about. So taking a more systems framework allows us to examine not just the goal of our system, but the way that our system sits inside of the world where it's a subsystem. Because you kind of always have this successive notion of my system that I care about is a subsystem of some context, some other system, and by taking the time to examine that context, we can be a little more informed about how we design our systems. And I like to talk about this concept of subjective choice of objective measure. So anyone who's worked in machine learning and data scientists often makes decisions about loss functions, other objective measures of something, whether I include a regularizer, whether this is the right loss function to represent the actual utility that's I'm maximizing or minimizing for in my optimization problem. These are objective functions. We call them that. But in fact, the process of choosing one is entirely subjective. It's encoding your human decision about the goal that you want the system you're making to achieve. And as we discussed earlier, it will achieve it at the cost of anything else. So this choice is actually one of the most sensitive points in the entirety of a system design. And I basically, when talking about engineering practice, point out that as an algorithm designer or a system designer, there's almost nothing more important than taking the time to formulate the problem right, something that Trent also brought up earlier. Now, what does right mean? Well, there's two kinds of right here. People get caught up in is my model correct in a sort of formal sense? Does it mean what really happens? And the answer is no, it never does. No model can be effectively granular enough to represent exactly how things work. So look at our Kirchhoff's laws and our circuit sort of equations, those are models. They're actually, if you go down far enough, they're wrong. All of our Newtonian physics is. Effectively, we look at models in terms of whether they're useful, and they're useful if they help us build things that work. And so on the question of, is my model right, it's actually more appropriate to ask things about whether my model is sort of inheriting the right goals, and is it fair? Fair is also a loaded term. In fact, the biggest problem with fair is that we can't really measure it formally, but we have sort of heuristics for understanding whether things are fair, and I'm a fan of the veil of ignorance, and I think it fits in very well with what we can do with algorithm design, precisely because it's easy in an abstracted model to ask questions about all possible starting points, or don't presuppose that I'm of type whatever. Consider what the system is like for all of the role types that you're defining, or consider against an abstraction of what it means to be an agent in the system, and ask questions about the system as it pertains to that sort of not presupposed actor. And I consider that to be the closest thing in these algorithmic design problems to working from the veil of ignorance. I think that one of the other things that gets missed is that there's actually often a big gap between the utilities of the individuals and the utilities of the community. In general, a temporal system of actors moving through the system are going to experience something very different from the aggregate system sort of ensembled representation of the state evolution. This is one of the reasons that we use agent-based models. It's also one of the biggest breakdowns in the current decision-making paradigms. This is from an article by Taleb, who talks a lot about this concept of non-ergodicity. Non-ergodicity means that your past observations of a system are not inherently indicative of the future observations of the system. This comes from nonlinearity. It comes from a variety of potential mathematical properties of the system, but our machine learning, our data science tends to rely on the fact that our past observations are sufficient to tell us about what might happen in the future, and that mathematical assumption is frequently broken. And so one way of being more robust is to try not to make that assumption in your design. Assume that you're going to achieve things that you haven't observed before, so that you don't sort of pin yourself into a corner or get blown up by black swan events. Sort of on the direction of wrapping up, I'm going to loop back to this concept of ethics and basically call out the fact that this isn't just like, oh, engineering includes ethics. Like, it is formally included in the sort of statements of these engineering institutions, like the IEEE, like the professional sort of bodies for civil engineering. In any place where what you're building is fundamentally going to touch humans and the well-being of some humans, physically, financially, or otherwise, is determined by the system, you're going to have some notion of ethics totally baked into engineering. And I'd like to point out that in this complex systems paradigm, we don't have quite the sort of level of control over what we're building. And so in the complex systems paradigm, we sort of come back to this idea that, we're not controlling the system or making it do anything. We're acknowledging that we're part of that system, and that our solution is less about making something happen and more about understanding the sort of structure and flow of the interactions and this evolutionary system. It's inherently more organic. So I would advocate for anyone who's interested in doing design in this field to actually go back to more organic models, even though we're using formal frameworks and mathematical frameworks that are consistent with circuit design, actually bio-inspired methods of modeling, bio-inspired even bio-inspired economic models, where we look at things like their flows of value in ecosystems, are actually incredibly powerful and, in fact, necessary often for decentralized systems, because they are structurally much more like those mathematical models than they are like our sort of centralized, sort of top-down controlled systems. The way that we contend with the sort of long-term well-being of the system is always going to involve some maintenance. We discussed earlier that that's not inherently easy, but we always view these systems in terms of all of the rigorous work that you can do to get them deployed. What does it mean to continue to maintain them? And that's a bridge into governance topics, which we aren't going to hit today. But I would say in this context of evolution and bio-inspired models, we can think of this as a part of an evolving system. Then if the code itself doesn't have a means to evolve, even if that's humans in the loop as part of the system to help evolve it, our system will eventually break or our ecosystem will die out. So I view the protocol governance problem as actually the very definition of the adaptive maintenance of one of these token engineered systems. So that is the end of my talk. So thank you very much.
Thanks, Michael. Amazing as always. We do have room for 10 minutes of questions, so it's going to be a little bit of a discussion here. Let's start in the front.
What would be the efficient way to simulate a token model? Sorry. For example, you mentioned that you can use Juniper for creating a simulation, but also it's possible to make a simulation through smart contracts and run transactions through the smart contracts and see the result at the end. Which would be the best way, or combining them would be a good idea?
So the methodology that I'm doing here involves both through the process. So in the, let's go. In this slide, the one here, the light blue is the differential equation type of simulations based on Python, and the dark blue is where you're actually running what I call emulations, where the sort of smart contract code is part of the system. So the blue is essentially the way the world works, and the light blue is a model of how the world works, and the dark blue is that instance of the thing made which you're running and testing on. So you're still simulating, in a sense, the green, even when you're doing the smart contracts in the blue, but this is actually mapped out to represent multiple stages of sort of scientifically refined analysis of the system, and it connects with this V diagram, which is further back. So on the way down, you're doing the sort of simulations in Python because you're doing design validation and design testing and design iterations, but actually you're on the way up because you have to have fabricated something in order to do tests with the something in the loop. So you're doing these emulations and you're still testing so that you can have these feedback loops, but a lot of the traditional software engineering iterative loops are the blue with the gray feedback here, and so you're basically saying, okay, here's my design, I built it, and I run the test on the thing that I made, which is totally important. You should definitely do that. That's why those gray bars are here. The real addition with the simulations of these complex systems is that you can be a little bit more rigorous about the design in the sense of the circuit, where this is big web of interacting elements, and you could understand better how those elements interact before you take the time to fabricate them all. And that's where you're doing these design iterations in the sort of Python-based simulations, so that by the time you fabricate, you're already a little closer to what you needed to get to, so that you can do these faster iterations on the differential equations, and you get slower iterations when you're iterating on the code base itself.
Thanks for your talk, and especially how you incorporate complex systems engineering into the whole space. I have a question about models. Models can have pros and cons, and they all have their own biases. Do you look at models where you want to use the most useful one, or do we also look at various models at the same time in a comparative way?
So you always look at multiple. I think there's a couple places in the talk where that comes in. One of the most important is this one. Basically, anytime you choose your model, you're making some of these sort of subjective choices of the objective representation of your system. So we consider that always to be a choice from a set, and part of the reason the tooling actually allows for this is because we want to be able to iterate not just over sort of what the behavior was, but also the models of the behavior. So I might say, here's the intuitive narrative behavior. I might write 3 different models of math that represents that intuitive behavior and test all of them, because I have no idea which one of them is good. Ideally, this whole system safety thing doesn't say I'm predicting what's going to happen with my simulation. Rather, I'm doing a numerical thought experiment that says, oh, if these things are true, I don't know that they will be, but if they are, here's what I might expect could happen. And so what we're really trying to do is make sure that we have a design that's robust to as many possible representations of what might happen as we can think of or model.
Great, thanks.
Okay, thanks. One question. Like currently society has to deal with things like, financial crashes or runaway inflation, where we have kind of man-made systems, social systems, and we already have trouble dealing with that kind of stuff. Have you thought about how we might deal with kind of like token-based disasters of like a runaway tokenized systems that is causing a lot of issues?
Some, but I don't actually distinguish them in the sense that you describe those real-world versions of those problems. I mean, fundamentally, they're the same class of problems. So the complex systems discipline is actually an interdisciplinary community of experts from across, biological and social and technical systems. And when you go to their conferences, you'll go from a talk that's on literally financial crashes in South America to sort of a biological evolutionary system to a sort of engineering design problem in the same, in the same block of talks. And so I would say I've thought about it a lot, but in the general sense, like these mathematical models, when I was talking about ergodicity, non-ergodicity, and the sort of effect of achieving sort of resistance to black swan events, or understanding the system well enough that you're not just doing a data-driven model that is reflecting past observations, but actually building a model with some structural integrity that tells me something about some of these failure modes even though I haven't achieved them, and trying to be robust to them. And that gets into the kind of testing that we do with the simulations, is if we have these sort of analytical representations of the system, we can explore edge cases, try to determine the cases that break it, which means that we can rule out some of those possible crashes. And again, this is heavily a part of system safety in these physical systems. You can't rule it out completely, but systems that were designed with these same mathematical principles actually sort of regulate your power grids that, there's a lot of decentralization in them. And there are rolling blackouts. It's not to say that there are never failures, but the point is that the degree of protection is a function of the sort of effort to engineer against failure modes. And in fact, in the power grid example, I talked to someone who actually works with power companies, and apparently there are conditions under which it's preferable to actually let the power go out and to recover than to actually do what it would have taken to prevent it from going out in the first place. But the fact that they know that, have modeled for that, made that decision, is a far cry from, oh no, it happened, what do I do?
Yep. Yeah. Yes, so something that's quite common in complex nonlinear systems, especially chaotic systems, is to represent what can happen as kind of a phase space and rely on an attractor, which is basically either a type of behavior, like a loop of behavior, towards which the system is going to converge. Based on what you did, with token systems, is that something first of all, is it tractable? You can actually do?
It is actually. It's hard, and it's sort of built on the mathematical frameworks, not necessarily on the simulations you can use to validate whether you've achieved those things under different assumptions. But the analytical approach involves these things called Lyapunov functions, which are used in multi-agent control systems that I've worked on in the past, and They basically represent these sort of generalized energy functions that you can use to characterize the system. You don't necessarily code them into the system. They're representations of a notion of energy that you can view as associated with the system, and you get proofs through essentially dissipation or energy conservation under these functions. But to be clear, to actually engineer them, you have to do analytical work, and it's about making assumptions about the behavior as a abstraction. You say, let me look at all possible actions, and then let me look at the way all possible actions affect my energy function. So if you want this energy to dissipate at any time, you would basically show that this energy function is strictly reduced by any legal action by any party. And that's the way that these types of analytical tools actually get applied, but it takes a next level of mathematical or controls expertise to have the sort of mathematical and sort of experience using them. I do advocate using them. I'm bringing them into my own design process. But for the general case, I would say they add a whole level of rigor, but they also add a level of difficulty to the design process.
Do either two small questions or one big question? Small one?
First of all, thank you for your talk. I'm just curious. I'm not exactly following the math, but I really like how you're gaining metrics from the code and using really rigorous scientific method. It kind of reminds me of Google Analytics, though. And I'm just my question is, what typically are the insights that you gain into the different protocols you analyze, and is there a class of insights generally?
Ooh, so from the analysis side. So this is sort of, I mostly talked about synthesis. So on the analysis side, the coolest thing that I found was, well, for starters, we don't need Google Insights because our public blockchains literally log everything. So we just go a little bit of a pain to unpack it, but you can have a full copy of the full history of, say, the Ethereum blockchain, decode it and analyze it. My favorite thing that we found was the sort of emergent of agents to fill niches. The coolest thing for us, we did some analysis of CryptoKitties. There's a externally facing feed to the party, the bot or agent that calls the birth of cats because it's computationally separated from the breeding process. And they basically give away 0.08 Ethereum to whatever agent is actually successfully responsible for basically paying the gas fees for the transaction that gives birth to the cat, even though the cat goes to someone else entirely. It's not a player of the game. It's a niche that came into existence in the Ethereum environment as a result of this externally facing incentive. And the thing that happened on top of that is agents actually optimized their response to this incentive by creating intermediate smart contracts that use the gas battery effect and also make multiple calls at the same time in order to sort of streamline their ability to capture these rewards. So by far the most interesting thing is emergent niche filling. We call those birth-giving bots midwives. And I expect to see this pattern evolve a lot more, that people are going to realize that you can essentially subcontract computation by providing rewards, and then we can actually reasonably expect sort of agents to come and fulfill that niche. And I'd like to see that more in the design process. We account for it in the autonomous model for giving the creation of the art. Actually, the idea would be there's a code that's going to be the generator function that's going to give rise to the art, but in order to make the transaction that creates the NFT, much like in the CryptoKitties example, someone who doesn't have an other benefit is going to need to call that. And so I'm hoping to see it in that ecosystem again, and more broadly, I see it as an important way to sort of build this truly decentralized ecosystem.
How do you account for irrationality of agents, and do you account for it in a formal way?
So two answers. One is in the analytical work, we very specifically assume nothing about them, meaning their action space, which is that which they can do, is used rather than what they will do, which means there's actually no notion of irrational or irrational at all at the analytical phase. When you get into writing simulations, the first way that I tend to do it is I characterize sort of a mixture of behavioral models that aren't inherently rational or irrational. In some cases, we could define sort of noisy agents that just do random things, or we can define agents whose only goal is to break the system, which you could say is rational with respect to the goal to break the system. But we can essentially think about agents in terms of some well-defined objective that's specific to them, in which case they are rational in the sense that they work with that objective, but you can be rational with respect to an arbitrary objective, then I can code up an agent that you would think was irrational. Or if you want to go really broad, you can do things where agents are like machine learned or are essentially learning on the fly anyway, in which case we don't even know how they're going to behave.
Thank you so much, Michael. You'll be here all day. Maybe we should. Thank you.